Pause for a moment and consider what's happening in the space around you right now. Illumination fills every corner. Objects become visible because electromagnetic radiation enters your visual organs. The explanation seems straightforward enough, yet when you examine what's actually occurring, the simplicity evaporates into something far more bizarre. At this precise moment, electromagnetic waves from every surface in your vicinity are propagating in countless directions simultaneously. When your gaze lands on any object, radiation from that object completes its journey to your retina. Simultaneously, radiation from you is completing the reverse journey to that object. Electromagnetic waves are intersecting everywhere, overlapping, occupying identical spatial coordinates. How does this work without creating complete chaos? How can trillions of electromagnetic rays traverse space in all directions without everything becoming an incomprehensible blur? How does your visual system extract a coherent image when this pandemonium is occurring? And this is merely the wavelengths your eyes can register. And now, as you're processing these words, radio transmissions are penetrating this space. Television broadcasts, thermal radiation emanating from your body, radar signals from aircraft, X-ray photons from astronomical sources, all traveling through the identical space, through your physical body simultaneously, all fundamentally the same phenomena as light, merely operating at different wavelengths. So what is light, really? Not the sanitized explanation presented in educational institutions. That version is incomplete, possibly fundamentally wrong in ways that matter deeply. The authentic answer, what electromagnetic radiation actually is and how it propagates from one location to another, is so profoundly strange, so utterly unlike anything in our everyday experience, that when you finally grasp it, your perception of reality transforms permanently. Let me reveal it to you. Picture yourself beside a swimming pool. Multiple people are diving in. Each entry creates disturbance. Splash, splash, splash. Waves propagate across the water surface. Ripples intersecting with ripples, creating apparent chaos. Now imagine a remarkably perceptive insect positioned at the pool's corner, simply remaining stationary, detecting the water's movement against its body. The waves arrive from different vectors, different rhythms, different intensities. Could this insect, merely from sensing these wave patterns, reconstruct what's happening throughout the pool? Could it determine who entered the water, where they entered, when they entered, the complete activity across the entire pool? Sounds impossible, yet in principle, yes. All that information exists encoded within the waves. That's precisely what you're doing right now. When you observe anything, the electromagnetic radiation reaching your eye consists of waves, analogous to the pool, except existing in 3 dimensions instead of 2 dimensions. Waves traveling in all directions, intersecting, overlapping, a complete mess. And your eye, it's a small aperture, approximately 1/8 of an inch. A tiny detector, particularly sensitive to waves arriving from specific directions, less sensitive to waves from your peripheral vision, unless you rotate your eyeball to reposition that aperture. From this chaos of waves, you extract an image of the world. You determine what you're observing from a distance. And here's what's truly extraordinary. When you're looking at me, someone positioned to your left can simultaneously see someone positioned to your right. Electromagnetic radiation is propagating this direction. Electromagnetic radiation is propagating that direction. Waves in all directions, a complete network. It's not like projectiles passing through each other. It's something causing the electric field to oscillate like water height fluctuating up and down. Some quantity vibrating everywhere. The combination of motions so elaborate and complicated that the result produces an influence that makes you see me at the same time completely undisturbed by the fact that there are influences making that other person see someone else entirely. There's this tremendous mess of waves throughout all of space. Electromagnetic radiation bouncing around the room, propagating from one object to another. Most objects don't possess 8-inch apertures to detect it, so they're not interested. But the electromagnetic radiation is there regardless, reflecting off this, reflecting off that, all occurring simultaneously. And yet, we can extract meaning from it with this instrument called an eye, the invisible ocean. But that's just the wavelengths your eye detects. Consider those pool waves again. Some are large, some are small, some are slow, long swells. Some are quick, short ripples. Your hypothetical insect might only study waves within certain size parameters. It turns out the eye only utilizes waves between specific lengths too. Except those lengths are microscopic, approximately 1/100,000th of an inch. What about the longer waves? The slower swells, those represent thermal energy. We perceive them infrared radiation. Our eyes don't register them, but they're present. Pit vipers, snakes inhabiting desert environments, possess a specialized organ that can register these longer waves. They can detect mice radiating body heat, perceive them in complete darkness by detecting infrared. We lack this capability. Our eyes aren't constructed for it. And the waves extend longer, much longer. Radio waves, identical phenomenon as light. Exactly the same kind of wave, just longer. Much longer, which means right now, positioned where you are, there's not only the electromagnetic radiation making you perceive this content, there's also information from radio stations, Moscow radio broadcasting at this very moment, signals from Peru, radar from an airplane determining its position, all penetrating this room right now. Plus X-rays, cosmic rays, all the same kind of waves, exactly the same, just shorter, faster vibrations. It's all genuinely there. You don't believe it? Acquire a piece of wire connected to a receiver, a radio. The electrons in the wire get displaced back and forth by the electric field, oscillating at precisely the right speed for certain long waves. Adjust the controls to synchronize the oscillation, just right. And you hear Moscow radio, then you know it was there. How else did it arrive there? It was there all along. You only notice it when you activate the radio. All these phenomena penetrating the room simultaneously. Everybody knows this, but you have to pause and contemplate it to really appreciate the pleasure, the inconceivable nature of it all. For centuries, natural philosophers argued about what light truly is. Newton declared light is composed of particles, miniature projectiles shooting through space. Corpuscles, he termed them. That's why light travels in straight trajectories. That's why you can't bend it around obstacles. Hawkins disagreed. Light is a wave, he insisted, like sound, like ripples in water. Waves spread outward. Waves interfere with each other. They couldn't both be correct. Could they? The debate raged for 2 centuries. Then came experimental demonstrations that appeared to resolve it. Direct light through 2 narrow slits. What do you observe on a screen behind them? If light were particles, you'd observe 2 bright strips, projectiles passing through slits. But that's not what occurs. You observe a pattern, bright bands and dark bands, interference. Exactly what waves do when they overlap. When 2 wave crests meet, you get brightness. When a crest meets a trough, they cancel. Darkness. Light must be a wave. Case closed. Except then someone constructed a detector sensitive enough to capture individual photons. And what occurred? Click, click, click. Individual arrivals like bullets, like particles. But wait, send them through one at a time. Surely a single particle can't interfere with itself. It does. 1 photon at a time, and the interference pattern builds up. Each photon seems to propagate through both slits like a wave. So which is it, wave or particle? Here's what most explanations won't acknowledge. It's neither. Light is not a wave. Light is not a particle. Light is light. We don't possess a term for it because we don't have anything like it in everyday experience. We attempt to describe it using familiar concepts. Waves, particles, but those are merely approximations, crutches for our imagination. The reality is stranger. Photons are real individual quanta of electromagnetic radiation. You can enumerate them. They make detectors click, but they don't behave like miniature bullets. They behave according to quantum mechanics, which means they explore all possible paths simultaneously, like waves spreading outward. When you attempt to observe which slit a photon traverses, the interference pattern disappears. The wave behavior vanishes. You get particle behavior instead. Not because photons are sometimes waves and sometimes particles, but because asking which slit is asking a particle question. And when you ask particle questions, you get particle answers. The photon doesn't decide to be a wave or a particle. It's always itself a quantum object. What changes is how we choose to measure it. This isn't philosophy. This is how nature actually operates. And it's far stranger than anyone imagined. So if light isn't particles flying in straight trajectories, why does it go straight? Here's where things become beautiful. Light takes the path of shortest time. That's Fermat's principle, discovered in the 1650s. Out of all possible paths light could take from point A to point B, it takes the one requiring the least time. Sounds simple, but the consequences are extraordinary. Why does light go straight in air? Because a straight line is the shortest distance. And if light travels at constant speed, shortest distance means shortest time. Why does light bounce off a mirror at equal angles? Because that's the path of shortest time between source, mirror, and destination. You can prove it with geometry. The quickest way to get from point A to a mirror and then to point B is to hit the mirror at exactly the angle where the two angles are equal. Now here's where it becomes interesting. What happens when light transitions from air into water? In water, light travels slower, approximately 25% slower than in air. So if you're on land and someone's drowning in the water, what's the fastest way to reach them? Straight line? No. You run faster than you swim. So you should run a bit further on land, even though it's a longer path, to spend less time swimming. That's exactly what light does. It doesn't go straight when entering water. It bends. It travels farther in the fast medium to spend less time in the slow medium. This bending is called refraction. The mathematics works out perfectly. The angle of bending depends on the ratio of speeds in the two media. This is Snell's law, but Fermat's principle explains why Snell's law works. Once you understand that light takes the path of shortest time, all sorts of strange phenomena make sense. Mirages on hot roads. You see what appears like water on the pavement ahead, but when you arrive there, dry as bone. What you're seeing is skylight reaching your eye by a curved path. How? The air just above the hot road is hotter than the air higher up. Hot air is less dense than cool air. Light travels faster in thin air than in dense air. So instead of coming straight down from the sky to the road, the light can save time by curving through the region where it goes faster. It dips down into the hot layer, speeds up, then curves back up to your eye. You see sky. But the skylight is arriving from the road direction. Your brain interprets that as a reflection, water. Here's another one. When you observe the sun setting on the horizon, it's already below the horizon. Earth's atmosphere is thin at the top, dense at the bottom. Light from the sun travels slower in dense air. So instead of coming straight to your eye, it curves. It stays higher in the atmosphere longer, where it travels faster, then bends down to reach you. The sun appears to be on the horizon, but it's actually already well below it. The atmosphere bends the light. We see phantoms of the sun. Now let's create something useful. A lens. Suppose we want all the light leaving point P to arrive at point P prime. Focus it. Bring it all together. Light going straight from P to P prime. Fine. That's one path.
But how do we make light that goes to some other point also end up at P prime? How do we focus? If light always takes the path of least time, it won't want to take all these different paths. It'll choose the fastest one, unless we make all the times equal.
That's the secret. A lens makes all paths take the same time. Here's how. Glass slows light down. So if we take a ray that would naturally go a longer distance, we can insert some glass to slow it down. Make up for the extra distance by adding extra delay. We end up with a piece of glass thicker in the middle, thinner at the edges. All paths straight through the middle, angled through the sides, take the same time. That's a lens, a device that equalizes travel times. Same principle works for mirrors. Want to collect starlight from billions of miles away and bring it to a focus? Make a curved mirror. Shape it so that light hitting anywhere on the mirror takes the same total time to reach the focal point. That shape is a parabola. The 2,000-inch Palomar telescope uses exactly this principle. All optical instruments, telescopes, microscopes, eyeglasses, work by manipulating travel times, making some paths faster, some slower, to control where light goes. But here's the deepest question. How does light know which path takes the least time? Does it somehow sense the nearby paths, check them against each other, choose the best one? The answer is yes. In a way, that's the feature you can't explain with straight lines and rays. That's where wavelength comes in. The wavelength tells us approximately how far away the light must check other paths. It's hard to demonstrate with visible light because wavelengths are so short. But with radio waves, say 3-centimeter waves, the effect is larger. Position a source, a detector, and a slit between them. Radio waves propagate from source to detector through the slit. Fine. Make the slit narrower. Still works. Now move the detector to the side. The waves won't go there through a wide slit. Why not? Because they're checking several paths nearby, and those paths correspond to different times. The waves interfere with themselves, cancel out, but close the slit down to a very narrow crack. Now there's only one path available. The waves have nothing to compare against, so they take it. With a narrow slit, more radiation reaches the sideways detector than with a wide slit. You can do this with light too. Here's how. Find a small bright light, a distant street light or sun reflection in a car bumper. Hold 2 fingers in front of one eye. Look through the crack. Squeeze your fingers together gently. The light, which was a small dot, becomes elongated, stretches into a line, and if you look carefully, you'll see fringes, bands along the edges, colors. Why? The fingers are very close together. The light spreads out at an angle. It comes into your eye from several directions instead of one. This is light, not going in straight lines, light checking nearby paths, light behaving like a wave. So what's actually happening? What is light really doing? Here's the modern understanding, the quantum mechanical picture. Light is composed of photons, real particles. Detectors click when they arrive. The brightness of light is proportional to the number of photons per second. But photons don't travel like bullets. When a photon goes from A to B, it doesn't take one path. It explores all possible paths simultaneously. For each path, you draw a little arrow, a complex number. The angle of that arrow is proportional to the time that path takes. The faster the light oscillates, the more the angle rotates. That's frequency. Different paths take different times. So the arrows point in different directions. Now add up all the arrows, all possible paths. The probability that the photon arrives is proportional to the square of the length of the sum. Here's what happens near the path of least time. The time doesn't change much as you vary the path slightly. So arrows for nearby paths all point in roughly the same direction. They add up, reinforce each other. Far from the path of least time, small changes in path produce large changes in time. The arrows point all over the place. They cancel out, form a tight spiral. Almost all the probability comes from paths near the minimum time. That's why light follows the path of least time. Not because it only takes that path, but because all the paths far from it cancel out through interference. This explains why you can block part of a mirror, and it still reflects almost normally. You're just removing some of the arrows from the spiral ends. The central cluster near the minimum time path is what matters. This is the connection between the photon picture and the principle of least time, between particles and waves, between quantum mechanics and classical optics. Light takes all paths, but only paths near the minimum time contribute significantly. Remember those pool waves, different sizes? Light comes in different wavelengths, and we give them different names. The longest waves, meters to kilometers long, are radio waves. AM radio, FM radio, TV broadcasts, all electromagnetic waves, just very long ones. Shorter, centimeters to millimeters, microwaves, radar. Shorter still, fractions of a millimeter. Infrared, heat radiation, what you feel from a hot stove. Then visible light, the tiny range our eyes detect, about 400 to 700 nanometers, 4 to 7 ten-thousandths of a millimeter. Blue is short, around 450 nanometers. Red is long, around 650 nanometers. Shorter than blue, ultraviolet, what gives you sunburn. Shorter still, X-rays, what doctors use to see your bones. Shortest gamma rays from radioactive decay and cosmic events. All the same phenomenon. Electromagnetic waves, oscillating electric and magnetic fields propagating through space. The only difference is wavelength is frequency. Different wavelengths, different properties. Radio waves pass through walls. Visible light doesn't. X-rays pass through flesh. Visible light doesn't. But it's all light. All electromagnetic radiation. All the same thing. And it's all in this room right now. Radio signals from thousands of stations. Infrared from everything warm. Visible light bouncing around. Ultraviolet from the sun. Cosmic rays from distant galaxies. All the same kind of waves. All coexisting. All passing through each other without interfering. A complete network of vibrating fields filling every point in space. So what is light? Not a wave, not a particle. Light is light. We don't have a word for it because we don't have anything like it in everyday experience. It's a quantum object. When you're not looking, photons explore all paths, interfere with themselves. When you detect them, they arrive as discrete quanta, clicks in a detector. Both are real. Both are true. There's no contradiction, just two aspects of the same quantum reality. We evolved to understand everyday objects. Things we can hold. Light is none of those. Light is something else. But we can understand it by following the mathematics and experiments, and they lead somewhere strange and beautiful. Think about what's happening right now. Photons from the sun, infrared radiation from everything warm, radio waves from hundreds of stations, X-rays from space, cosmic rays from distant stars, all passing through the same space at the same time. A tremendous mess of waves. And yet we can sort it out. Tune a radio and hear a single station. Look and see a coherent image. Everybody knows electromagnetic waves fill space. But you have to stop and think about it to really get the pleasure, the inconceivable nature of nature itself. When you understand what light is, really understand it, the world is far stranger than it appears. Far more beautiful. And that's what physics is about. Expanding our intuitions to grasp nature as it actually is. That's the beauty of it. The terrible, wonderful beauty of understanding.